Hello, everyone. This is another episode of Math Tutoring for Free. My name is Annika Williams, and today we're going to be going over an introduction to integrals. So let's start out. Okay, so an integration essentially undoes a derivative. So as you can see, oops, why did it do that? Let me get this. Okay, so as you can see here, we have the derivative of x with respect to time, of position with respect to time, is velocity. And if we were to undo that, we would say that the integral of velocity is position. So it's sort of like reverse engineering the whole deal. Same thing goes with acceleration. The integral of acceleration with respect to time equals velocity, and the integral of velocity with respect to time is position. Just the same way as the derivative of position with respect to time is velocity, and the derivative of velocity is acceleration. It essentially undoes a derivative. And you can say that it's respect to time, you could say it's respect to x or respect to y. You can take, just as you can take the derivative with respect to x, y, z, t, anything, you can take an integral with respect to x, y, z, t, anything. It's essentially the same concept, but just reverse engineered. So if we go over an example here, let's say we're going to take the integral of 2x, or let's say we take the derivative of x squared. That equals 2x. If you've taken Calculus 1 and you already know your derivatives, you know that's pretty straightforward, and that's the deal. So if we're to take the indefinite, sorry, these are not unspecified. This is supposed to say indefinite. Okay, so if we're going to take the indefinite integral, meaning there's nothing here that we're evaluating, we'll get to that in a second. But if we're taking an indefinite integral where there's just nothing from the bottom to the top of 2x dx, and remember to put the dx there, then we get x squared plus c. And c here is the integration constant. It essentially means that if you take the derivative of any constant, it's going to equal 0. But if you take the integral of 0, it's going to equal a constant. So if, let's say this was 2x, let's say that this was x squared plus, 7, and we're taking the derivative of this, then we would get 2x plus 0. So this over here, this number, essentially could be literally any number. It could be, infinity, it could be 0, it could just be, -1 or anything. That's why we put the integration constant over here after we integrate the phrase. So now we're going to go on to definite integrals. Gosh, my pen is being a little bit laggy. Definite. Okay, well, you can read that, I guess. Integrals. These are integrals where you can see you have an integration from a certain number 0 to infinity, and you read this sort of from bottom to top. So we integrate from, 2x dx from 0 to infinity. This partially comes from Riemann sums, because Riemann sums you also read it this way. So you say like the sum of something from n equals 0 to infinity, and you sum from 0 to infinity, but you read it from bottom to top. We'll go over how integrals relate to Riemann sums. Unfortunately, in calculus 1 and 2, you don't really go over Riemann sums. Or just summation in general is kind of like a multivariable calculus kind of ordeal for some reason, even though integration is based off of summing. But we'll get to that, how it relates. We'll just go over it briefly. So let's go over this example. So the integral from 0 to infinity of 2x dx is equal to x squared, as we calculated already up here. And this time, because it's a definite integral, we don't have to put the plus c. So remember that. If there's an indefinite integral, then you put the plus c at the end. If it's a definite integral, you don't need the plus c. So if we're gonna evaluate x squared from 0 to infinity, we essentially evaluate it sort of backwards from what we said before. And remember that you first plug in infinity into x squared, and then you subtract it here, right? Oops. We subtract it from when we put in 0 into x squared. So essentially, this is the first step, we subtract, and that's the second step, and that equals infinity. So yeah, that's essentially how you solve a definite integral. Not specifically with every single type of function, but this is the general format of, and obviously these numbers can be, the 0 from infinity, those can be anything. It can be a to b, it can be x to y, it can be 0 to x, it can be negative 2 to 3, or it can even sometimes be backwards where it's just 3 to negative 2. So yeah, let's go over the same thing with cosine of x and sine of x. So if we remember the sort of circular pattern of sine x and cosine x when we take the derivatives of each of them, the same thing happens if we take the integral of them. It just if the pattern, derivative of sine x is cosine x, derivative of cosine is negative sine x, derivative of negative sine x is negative cosine x, derivative of negative cosine x is sine x. So if we visualize that this way, integrating it is essentially just going backwards. So the integral of negative cosine x is negative sine of x, the integral of negative sine of x is cosine of x, and the integral of cosine of x is sine of x. So the integral here, as we just said, the integral of cosine of x dx is sine of x, and don't forget to put the plus c. And if we were to check, we take the derivative of sine of x with respect to x is cosine of x. And if we were to even, check this way, gosh darn, why is it doing this? Sine of x, seriously, sine of x plus derivative of a constant with respect to x with respect to x, then we still get cosine of x plus 0, which is just equal to cosine. Oh my god. Cosine of x. Alright, so let's go over a larger example. We already know the rules of derivatives. If you, add a couple derivatives together, you can separate, essentially, kind of like here in the integration. If you have, let's say, e to the x plus x squared minus sine of x, you can, integrating from 0 to pi, you can essentially separate these integrals and integrate them integrate each phrase or function, I guess, separately, and then just keep them added together. So, that's the first step, essentially, of integrating. As we know, the derivative of e to the x is just e to the x, so if we take the integral of e to the x, it's just going to be e to the x. So yeah, now we have e to the x dx, the integral from 0 to pi of e to the x dx plus the integral of 0 to pi x squared dx minus the integral from 0 to pi of sine x dx. And what we're going to do with this is we're going to take the integral of each function. So here we have e to the x, right? And this line here means that it's evaluated from 0 to pi, essentially. That's just kind of what it means, if you don't already know that. And then the next one is 1/3 x cubed, because if we're to take the derivative of 1/3 x cubed, we would get x squared. The 3 comes down, 3 minus 1 is 2, so then that's just x squared. And to kind of reverse engineer that, you add 1 to the 2, and then you divide 1 by this number that you get. That's kind of like the general deal with polynomials. So yeah, that would take some practicing for you to kind of like wrap your head around it. I would encourage you to do that. So anyway, then the next thing is we have negative, well, we have a minus sign here. So what we can do is we can keep the minus sign in front of sine x, and we can just say, oh, well, the integral of that is just cosine of x, which makes life much easier. So, we took the integral of that. Wait, did I do that right? So, the integral of negative sine of x is cosine of x. It's just positive. Yeah, either way it's going to be positive too, because if you have the negative sign here and you just take the integral of sine of x, you get negative cosine of x, and either way, negative and then negative is just a positive. So either way you get a cosine of x. It doesn't really matter which way you do it. And then after we evaluate all of these at 0 to pi, we get e to the pi minus e to the 0 plus 1/3 pi cubed plus cosine of pi minus cosine of 0. And then we get e to the pi minus 1 plus 1/3 pi cubed minus 1, and that's just e to the pi plus 1/3 pi cubed minus 3. And that final answer is 30.47, which is the answer to our definite integral that we first put up here. So that was kind of an example, like a very simple example on sort of like the addition, subtraction properties. We might go over multiplication and division later. There's a couple of rules for that, which I don't think we're going to be able to fit in this video. Alright, so as we know, derivatives are essentially zooming in very far into, let's say, a curve, and approximating that point as a line. It's essentially taking the linear approximation of something across points. And you can do that multiple times. You can do it infinitely, an infinite many times, depending on how many points you have. Integrals are essentially zooming out and also still approximating, but also adding another element to it. Because integrals are essentially just the area under a curve, if we're talking simple terms. And remember when I was talking about Riemann sums and how this relates to Riemann sums? Gosh, where's my cursor? Okay, this over here is essentially what an integral is. So we take the sum of some function from n equals a to b, and we take the limit of that function, and that's, like, we take the limit of the sum, and that's what an integral is. Because if we weren't to take the limit, like if we were just to have the sum, we'd either come across over approximation of a curve if we have rectangles that we were to use to kind of just estimate the area, we would either over approximate or we would under approximate. But if we take the limit of the sum, then we're able to close together infinite amounts of rectangles close together, and that would essentially it wouldn't approximate the area, it would give you the actual area under the curve, because there's infinite amounts of rectangles that are able to go under the curve and give you the entire area. So, this is sort of what a Riemann sum is, but if we take the limit as n goes to infinity of a, where is my cursor, of a Riemann sum, then this over here is what we get, the actual area under a curve with infinitely small rectangles. It's sort of the same concept as like zooming in like infinitesimally, as in when you do in calculus, but instead you're adding infinite amounts of very tiny rectangles. So, there is a correlation between relativity, I guess, and this, because if you take the integral of a line, you get an area, and if you take the integral of an area with respect to x, you get volume. But if you take the integral of velocity with respect to time, area, time, space, you get position. If you take the integral of acceleration, you get velocity. So this is something that, I think it might be useful if you're very interested in relativity in physics. You could definitely use this as like a concept that like, oh, well, you can take the integrals of position, you can take it with respect to time. This is something that's like, it seems obvious when you're doing it, but there is a distinction and there is also a connection too. So don't mix up the two. Don't mix up taking the integrals with respect to x and integrals with respect to time, because you might get a very different result depending on your variables. Usually it's pretty obvious which one you're going to take the derivative of, but sometimes if you have like two variables, x and t, and they say, well, take the derivative with respect to position or with respect to x or time, then you kind of have to pay attention to that, so you don't accidentally take the wrong, or sorry, not derivative. If you accidentally take the wrong integral, then you're going to get a wrong answer. And it's not really going to make sense. So yeah, that was it for today. Next time we're going to be going over, I guess, gun physics, if you're interested in what that is. So yeah, thanks for watching. Have a lovely rest of your day. Bye.